Hey everyone, and welcome! I am absolutely thrilled to have you here today. In this explainer, we're going to unpack a truly elegant mathematical tool designed for complex decision-making. We're talking about the Weighted Product Model, or WPM. Whether you're an engineer selecting materials, a developer architecting software, or a business leader comparing vendors, you've probably faced data that simply doesn't want to cooperate. Well, today, we are going to learn exactly how to make it cooperate.
So let's map out our journey. We'll start by tackling the core problem of mixed variables, right through to the underlying math, and finally, we'll even talk about how you can code a web calculator to do all the heavy lifting for you.
Let's dive right into that very first hurdle professionals face when evaluating multidimensional problems. I want you to imagine you're buying a piece of heavy machinery, or maybe a massive server for your IT infrastructure. Ask yourself this: how do you mathematically compare a $15,000 price tag to a 5-second speed rating? It's the classic apples to oranges pain point, right? You're trying to weigh completely different units of measure against each other to find a clear winner. And let's be honest, human intuition usually just fails us here.
To solve this, we rely on a field of study called multi-criteria decision-making, or MCDM for short. This is essentially the mathematical processing of numerical values to figure out a ranking of alternatives based on multiple conflicting decision criteria. It's the foundational framework for everything we're discussing today. We are basically taking raw conflicting data and processing it to find a scientifically sound ranking.
When you are staring at a standard decision matrix, you'll see a mix of things. Let's say you've got 3 options and 3 criteria: cost in dollars, speed in seconds, and an abstract quality score from 1 to 100. If you try to use simple addition here, the math completely breaks down. You literally cannot add $15,000 to 5.2 seconds and 85 points. The massive scale of the dollars would completely drown out the speed and quality criteria, which basically renders your entire decision invalid.
And that brilliantly illustrates exactly why we need a better tool, which brings us to the weighted product model.
The absolutely crucial point here is that WPM solves this mixed unit problem by using something called dimensionless analysis. It's a structural method that completely eliminates units of measure. By structuring the math in a very specific way, the dollars, the seconds, the arbitrary score points, they all just vanish. We are finally able to compare those apples and oranges equitably because we've stripped away the conflicting units that made them impossible to compare in the first place.
Okay, so how does this mechanism actually function under the hood?
Well, instead of using additive utility, which just sums things up, WPM compares alternatives by multiplying performance ratios. And then, those ratios are raised to the power of their specific criteria weights. Now, I know that might sound a bit complex at first, but honestly, it is a remarkably elegant calculation.
Let's walk through the algorithm. It's just 4 clear steps. First, you determine the relative weights of your criteria, meaning you know how important is cost versus speed to you. Second, you calculate the ratio between 2 alternatives for each individual criterion. Third, you raise those individual ratios to the exponent of that criterion's weight. And finally, you multiply all those resulting numbers together. And here is the magic rule. If that final product is greater than or equal to 1, the first alternative in your comparison is the mathematically superior choice. It is just a brilliant way of mathematically proving superiority.
To really grasp why WPM is so clever, we should probably compare it directly to its older sibling, the Weighted Sum Model, or WSM.
The weighted sum model relies on additive utility. It normalizes data and just adds the scores together. It's the simplest method out there, for sure. But as we discussed earlier, it struggles mightily with mixed units unless it's heavily normalized beforehand. On the flip side, WPM's multiplicative nature seamlessly handles diverse data types. Because it compares alternatives as ratios and multiplies them, the structure naturally neutralizes the unit differences. You don't need any complex pre-normalization of the data grid.
Now, what's really interesting about this math is how beautifully it translates into software engineering.
Building a WPM calculator for the web is incredibly feasible. From a user experience perspective, it requires very low effort, just a simple grid for inputs. And under the hood, the computational engine can literally be written in less than 50 lines of basic JavaScript. Because it relies on straightforward ratios and exponents, there are no complex optimization loops, no heavy matrix algebra libraries required. It's lightweight, it's fast, and it is highly effective. When you map out the feasibility of WSM and WPM against heavier academic models like AHP, Topsys, or Electra, a clear winner emerges. WPM has very low math complexity and low UI effort.
Compare that to a heavyweight model like Electra, which has huge complexity and is almost never recommended for simple web apps, or AHP, which requires these complex pairwise slider questionnaires. WPM is by far the easiest to build cleanly and deploy rapidly for your end users.
In fact, because the data inputs for WSM and WPM are exactly identical, you just need alternatives, criteria, values, and weights. The absolute best software architecture strategy is to build a dual dashboard. You let the user input their data matrix exactly once, and your application calculates both the WSM and WPM rankings simultaneously. This gives the users side-by-side comparative analytics with virtually zero extra friction.
However, we have to be honest here. No model is perfect. We really need to impartially look at the theoretical limitations.
If you do build that dual calculator, you are inevitably going to encounter something known in the research as the contradiction rate. This happens when WSM and WPM yield completely different top rankings for the exact same set of user data. It's a real head-scratcher that forces the decision maker to ask, wait, which algorithm is actually telling the truth?
The trend here is fascinating. As the number of decision criteria increases, moving from a few to many, the contradiction rate between methods also goes up. When you're dealing with highly complex problems with dozens of variables, the odds that the additive model and the multiplicative model will disagree goes up significantly.
So why does this divergence happen? It fundamentally comes down to how multiplication handles outliers. A single extreme outlier, say an incredibly high cost or a spectacularly fast speed, heavily swings a multiplicative sequence in WPM. It acts as a massive multiplier or divisor. But in contrast, that exact same outlier in the weighted sum model only has an additive impact, which ends up being much smaller relative to the whole.
To try and account for this uncertainty and these extreme swings, researchers have explored variations, like fuzzy WPM. This essentially replaces exact rigid numbers with fuzzy triangular numbers, which are basically ranges of values. The whole goal was to see if softening the data inputs could create more stable, reliable rankings when uncertainty is really high.
But surprisingly, empirical studies show that fuzzy WPM actually performed pretty poorly in resolving these issues. It turns out that ranking abnormalities and contradictions remain a deeply complex, controversial issue in decision analysis. There is just no single perfect algorithm that solves every problem flawlessly without some mathematical quirks.
Which leads me to leave you with this final provocative thought. If a perfect mathematical ranking is ultimately an illusion, and different models can yield completely different winners from the exact same data, what is their real purpose? Do these algorithms actually make the decision for us, or do they simply hold up a mirror, forcing us to adjust our criteria and weights until the math finally reveals what we truly valued all along? Thank you so much for exploring the weighted product model with me today, and keep learning.